Okay, so it's 9:01. I think we should start. My name is Markus Diesmann of Research Center Jülich. I'm happy to see you back here after this wonderful evening yesterday. This is session number 8, and our first speaker is Gert Cauwenberghs, and he will talk to us about silicon and Memristive integrated neuromorphic systems for engineered natural intelligence. Welcome.
Thank you. Okay, so welcome to the morning session. So we dive right into it. So neuromorphic engineering has been around for quite a while now, but let's motivate some of the really pressing issues that we're facing here. Sure enough, we had fantastic advances in AI, or whatever you call it, deep learning, AI, neural networks, whatever it's called. And we get this amazing improvements in the performance of those AI machine learning systems. But they come at an amazing, even more amazing and alarming cost in terms of the computation effort that is required just for learning the tasks. If you look here on the axis here, the vertical axis, sure, we get a improvement in the error rate, but you get on a log scale even a much more alarming rate of increased computations, and on the top axis here, energy consumption, or I guess carbon footprint of all this. And what is especially alarming is that now the computation involved is taking energy comparable to an entire month of a major city. So clearly this is not sustainable, and so we as engineers, we can also be green or eco-engineers because we can make really great contributions by making the hardware that we're developing much more energy efficient. It will have an impact on our carbon footprint. And so it makes sense to consider then the energy footprint of compute, and you can define that in several ways, but you can look at energy per operation, and that's the axis here. Right, so that's your, I guess so the lower axis here, as you can see, of course, the higher the worse. And the converse of that, the reciprocal of that is then the compute per energy, or the throughput per unit's power, right? And you see this massive spectrum, or this range of scales here between the theoretical limit, right, the Landauer physics-based, which you can understand how much energy does it take to keep one bit in a memory or do the compute equivalently. You need at least the energy barrier to be thermal energy, otherwise you just lose information. The SNR will go to 0. In fact, there's a factor ln2 there if you care about it, but still, so those are amazingly low energies, and looks all great, but this is in practice what has been there, not the latest chip, but still a representative metric, right? So there you have, basically here you're talking about picojoules or nanojoules versus then the 10 to the minus 21 or so joules in theory. And so it makes sense to consider how's the brain doing. Well, the brain on the spectrum is somewhere in the middle, closer to the theoretical limit, not quite there, for many good reasons. The brain doesn't operate at an SNR of 0. And so you can arrive this femtojoule per synaptic operation, and that's because our neurons fire typically between 1 or 10 hertz, let's say 10 hertz. We have about 10 to the 15 synapses, so each synapse is activated 10 times per second, so that gives you 10 to the 16 synaptic operations per second. And roughly speaking, our brains dissipate about 10 watts of metabolic power. And you can argue, in fact, the fact that some of us have hair on our skull shows that our brain is so efficient in computing that it requires even some hair to insulate and then keep the skull warm. So there's an upper bound. But so take the ratio of the two numbers, you get a femtojoule per synaptic operation. And so how do other systems perform? So you can say all the advances you have had with whether it's GPUs, FPGAs, right, have only gotten us 1 or 2 orders of magnitude better, and that's because the memory has been the bottleneck. That's where all the compute is stuck. The slow interaction between the compute, fast compute, centralized, and then slow but vast memory. And even the advances with high bandwidth memory, etc., right, have only gotten this a little better because the cost of getting a bit in memory is still in a pico joules range. Right, and so the obvious thing to do is compute in memory, where you bring the memory and the compute closer. In fact, you bring the compute in the memory as opposed to bringing the memory to the compute, and that's basically the paradigm that we have heard about in this conference here several times. And so they can get picojoules or so per operation. You can even push this further if you do things, I guess, if you optimize everything. So even with Memristive, right, this resistive RAM or other technologies, you can get down to femtojoules. So now within an order of magnitude, say, of what the brain can do in terms of nominal efficiency. And you can even push it further. So by even recycling the energy adiabatically, right, at resonance between electrostatic and magnetic energy, you can even push it further beyond even what the brain is doing. Still far away from fundamental limits, but so I'll highlight some advances where we can actually at least getting better than the nominal efficiency, with all respect to what the brain is doing. The brain is doing much more than just multiply cumulates, but in terms by that metric, we can actually, in principle, beat that metric. So, and this conference here is about neuromorphic engineering. Let me say just a few more words, and we have all heard about it now several times. But it's important to stay close to the physics, and that's how Cauwenberghs really started the field. Listening to the electrons or the holes and that you have in the silicon, what they're doing, and taking inspiration from biology, extremely important. Let's keep that in mind. More so than just the algorithms, but also how the brain is organized and the fundamental physical principles by which it advises, right? And so that's important to consider, along then with principles of learning and adaptation that will allow it to operate at intrinsically low precision at the device level, and you get really great performance at the system level owing to the organization and the adaptive nature of the elements. So that's the premise, and over the years, the field has evolved, in fact now 30 or almost 40 years ago. And the principle has been here to counter the typical analysis approach in neuroscience, basically reductionist approach, trying to resolve function at lowest possible level of scale in order to fully understand what is happening there, right, the analysis. And as engineers, we're doing the conjugate synthesis, build things from the ground up, and this way we can now synthesize systems, once you abstract them at the lower levels, that can reach the whole level of representation. And those two can work in concert, and in fact, neuromorphic engineering realizes that at each level of scale, there are those isomorphisms, physical isomorphisms, between the thermodynamics that happens, for instance here, right, at lower level here, at the ion channel level, but even at the higher levels here, networks. You can hear about Boltzmann machines, right? And so those have been very powerful in the latest advances in machine learning, variational autoencoder, etc. Right? And there's also the Boltzmann energetics in those networks, spin glass systems that you can analyze. So in the neural analogy. And so let me actually give a specific example of what triggered much of the advances as Cauwenberghs really highlighted this at the very beginning of the onset, that you have this almost exact equivalence between the thermodynamics of how electrons or holes move through a channel of an MOS resistor versus how ions move through ion channels, right, through membranes of cells, of neural cells. And this is amazing that you get almost the same exponential dependence, exponential because in the subthreshold domain, so you're dominated by the Boltzmann physics, right? As you get this energy distribution that is this exponential in voltage, right? And so this barrier implies that you get currents and conductances that are indeed exponential in this gap that you have, right, between source and drain, the channel, and the gate. And so sure enough, even with this ions going through ion channels, which are also, even though the physics is totally different, the substrate is totally different, ions versus electrons, right, in aqueous media as opposed to metals. The physics is similar because the protein folding mechanism also obeys the same fundamental limits, diffusion and drift balance that gives you Boltzmann distributions. And you can get this amazing high orders of magnitude exponential range, right, of conductance versus voltage that biology is exploiting. In fact, look at the slope. It's even much steeper than the slope that you have in silicon. So biology has figured out how to get subthreshold slopes, right, that allow it to operate at 100 millivolt of power supply as opposed to the 1 volt or so power supply that we have in silicon systems. So there's definitely good reason to look at how biology is doing things, right? And that's just one of the realizations, but then you can build systems that physically emulate, right, what the nervous system is doing. For instance, here in the retina, you can model, all the pixels that you have here in the silicon retina corresponding to the photoreceptors that you have in the actual retina, and then different layers here of horizontal cell, bipolar cell, etc. Right, and eventually then your ganglion cells, which are then the spiking neurons that convey the rest, that convey the information that is acquired on the focal plane to the rest of the brain. And this is intrinsically a spike code, but the circuits before that actually are totally analog and continuous time. And so this is great work done by Cobain and his team many years ago. The field of silicon retinas has really taken off since then. And you have heard of dynamic vision sensors. The concept is similar, but it's more of an engineering perspective. Adding a few more resistors along with your APS active pixel sensor. Now you can actually do change detection right there in the focal plane. Threshold up and down change detection, and then this can be efficiently coded, communicated. So you only send bits actually bits of information when something changes on the visual scene. So that's the general premise, right, of at least from the sensing side, of how to emulate intelligence of biological systems. And of course, you can extend all this then to doing processing, cognition, and the same code, the spike code, right, has been the language of how chips, these neuromorphic chips, communicate with each other. Just the same way that you have different regions in the brain where you get the white matter communicating with the gray matter at that scale. In addition, so that's basically the address event representation, right? That basically allows you to then build reconfigurable systems, right? Where you have basically right now having real wires between neurons. Implement synapses, you have virtual wires basically by sending addresses around. And you have already heard this at the conference several times. I won't belabor this, but so you can make this all reconfigurable and then implement the connectivity of your network after you fabricate a chip by changing entries in the table, in your lookup table for each presynaptic action potential, figure out what are postsynaptic destinations and also the parameters of that, right? So that's the premise that the field has gone into over the last 20, 30 years. And so this way you can build scalable, large-scale systems that can emulate biological intelligence. So there are a few issues that are important to consider. So 30 years later, we're facing still challenges in realizing large-scale systems, and scalability is always very much of an issue. So here in this, right, so considering the very hard tasks that we're trying to solve, and hard is surprisingly simple in our minds because for us it's effortless to just walk around in a room, or for flies to navigate, avoid the fly swat. Those are actually complexities up here, whereas simple task or even hard tasks in, say, the game of Go would be somewhere here. tic-tac-toe is probably there, the game of chess there, and so, right? So we have an elastic scale here of complexity, right? So search tree breadth and time, power to the depth. On the log scale extends quite largely. And here on the horizontal, on the vertical axis, you have the cost, right, of what price do you pay to achieve your task, right? And so on the log scale, things look simple. And with Moore's law, right, that's advancing every 2 years, you're doubling basically the number of transistors. That basically means we have been inching up this axis here over time. And sure, we were able to do better things, and AI, artificial intelligence, has been able to do greater things over time, but in a most linear fashion, or even supralinear fashion. So the cost has been supralinear. Mostly because if you're doing deep, exact search, you're, even with dynamic programming, etc., you're really limited at, I mean, if you want to get the exact answer, there's no way around the complexity that you have, the combinatorial complexity that you have. So neuromorphic engineering, or what we call this parallel distributed processing, that started about 30 years ago, takes a different approach, which is more analogical as opposed to digital, imprecise, you may say, but at the system level, actually quite precise. And basically, where you look at patterns as opposed to looking at precise, I guess, symbolic concepts. And so that there can have a much more favorable trade-off. So most of the tasks done by neuromorphic engineers have been around this place here. We can do things much better just on the computer. But as we get into harder problems, that's where the scaling advantage will play out. And so our task is really to push in that direction, do big problems, and then use deep learning and other approaches that can then abstract from the complex worlds, the lower dimensional representations, and efficiently implement them in hardware. So there are two complementary objectives that we need to accomplish here. So one is, of course, we have to being able to abstract the world into lower dimensional representations, the deep learning. But equally important is then to advance the efficiency by neuromorphic engineering. So being able to do everything at low power. We still want to do everything at, well, so the brain does about 10 or 15 static operations per second. There's probably no way that you can implement truly intelligent or general artificial intelligence unless you have systems on the same scale. Otherwise, evolution would have gotten rid of most of your brain. Right? And so then it's important to, in order to scale this sustainably, is to do this at very low power. And so power, minimizing power or minimizing energy per operation amounts to right? Well, energy per task amounts to minimizing energy per operation times operations per task. And those are, again, complementary here, right? So one endeavor is to improve the device physics as well as the organization of the architecture and the device physics to accomplish lower femtojoules per static operation. That's where we're going as a target for what the brain is doing. But also at the same time, you want to minimize operation per task, and that's more of an algorithmic approach where you go for deep learning or whatever you call that, I guess algorithms that will get you there. And those are complementary endeavors, and it's important to do both at the same time. You can't do one well without knowing the other. And that's why we have this community, that's why we're all here. We have neuroscientists, right? We have, in fact, yes, we have neuroscientists, computer scientists, cognitive scientists, and on the other side we have physics, nanoengineers, electrical engineers, and etc. Right? That in order for us to accomplish those difficult tasks. And I just highlight a few important ones here. So we definitely need to get density. Ideally, density is comparable to what the brain is doing, and use then techniques for lowering the energy that it takes for doing the compute. But also make sure that we can get scalable interconnects, take care of the white matter as much as the gray matter, and then to get enough data in order for us to train those systems at scale. So those are the different challenges that we have here. So here is an overview of not the latest, but a snapshot of some of the larger reconfigurable neuromorphic systems, and those are all reconfigurable in the sense that you can change the architecture of the network after you fabricate a chip. So it's not a dedicated chip that's just one thing. So those all can be reconfigured dynamically. And they're also large scale. basically at least a few hundred neurons up to millions of neurons. And you can recognize several systems here, the Spinnaker system. So now there's Spinnaker 2 also here in Dresden. Louis, there's IBM True North, the first system that reached 1 million neurons. Now there's a North Pole 2 with a different system. We have Intel Louis, which there's now Louis 2, right? So the numbers have been comparable in terms of efficiencies, what they accomplish. And then the analog systems. You have the Facets Brainscale Heidelberg system, still quite powerful in what it does. And the Stanford Neurogrid, so they're 65,000 neurons. At UCD, we have the IFAT system, integrated file rate transceiver. I'll see a bit more of that. And also here at ETH Zurich, the Rolls processor, right? If you look at all these different systems, so they get around one metric of goodness is then the energy per compute, and so that's in the order of about a few tens of picojoules per synaptic operation. And so that's orders of magnitude higher what the brain is doing. But it's important, in order to make advances there, it's important to realize that most of that is been limited still by the slow access between memory and compute, and there can be this important consideration to get the compute in the memory. But there's more than that, because if you really want to go for scale, it's not sufficient to take care of the gray matter. You also need to take care of the white matter. So the gray matter is the compute. Those are the synapses that you have in your brain. And most of what we have in our brain is not the gray matter, it's the white matter. That's the communication. Communication is extremely important to get data from one place to another place. We have two hemispheres, and so even though not every neuron from the left talks to the right, there's a very important fiber bundle between those two, right, that communicates. And so you have almost a small world model in your brain as a hierarchical construct, right, that gets the data from one place to the other place, right, in a hierarchical fashion. And so three base architectures are important to realize this expandability, be able to get anywhere with a few hops through your architecture. So that's a typical, that's the way how the internet is organized. At the same time, you want great flexibility in having arbitrary connectivity between your right, because neurons, and that's the gray matter, the synapses, right? And so, yeah, we want to have great crossbar arrays. That's what you do here. But also, you want to be able to hop across those crossbars in a very efficient manner. And those are the three base architectures. And so, combining those with something like hierarchical additive routing is something that I'll say a bit more about. That's extremely important. So, yes, you can get both accomplished at the same time. In terms of scaling is great because you can get really femtojoules per operation in the gray matter for your synapses up here, right? And you can also then get picojoules per operation for neural event communication along distances. And the farther you go, the higher energy it is, but the sparser you have them, because most connectivity in the brain is locally dense, globally sparse, right? So then energy-wise, it still plays out, right? Given there are many more synapses than neurons, still, if you relate it per synapse, you can still get femtojoules, even though you get picojoules for sending data across, and even larger energy for sending it across long distances. And so here's an example of I mentioned the IFAT system. And so the principle actually is quite important, I think, that you can do much of the analog dynamics of how membranes operate, then in dedicated circuits, arrays of neurons that emulate the physics as Carver told us, right? The physics of ions, conductances, capacitance, etc., right? And can implement synapses and the excitability of the neuron. And so when a neuron fires, it sends an event out through this address event routing architecture. Right, so with its address, and then you go through tables outside to figure out postsynaptic destinations, and as well as your some parameters, conductance, etc., right, of your synapse, and that is then routed into the networks. So where you have the synaptic terminals, this time multiplex synaptic terminals, where they implement the rest of the dynamics. So they can have internally analog continuous time dynamics of your networks, whereas you have digital reconfigurability on the outside, right? And as well as learning. You can also do learning then on the outside. And of course, that's great, but this is reconfigurable, but not quite as efficient because most of the energy then is taken in the getting the data out and in of the system. So, so how do you go then from the tens of picojoules down to the femtojoules? Well, it turns out that one of the greatest neuromorphic synapses you can imagine has already been done by this multi-billion-dollar industry that now does all those. We call them emisters. Others call them resistive RAM or phase change memory. There's a whole class of non-volatile, mostly digital memories that can be repurposed as entirely analog memory simply by using the same. So you have to say this resistive element here. You have a word line selector, right? And so you can repurpose your word line here as your presynaptic action, right? Your action that basically activates this postsynaptic conductance, right? And that will then induce the currents that are in the dendrite that you have here in the bit line. And so the element is exactly the same. So in fact, whether it is phase change memory or, right, those are actually analog elements. You can change your conductance in a graded fashion. It's non-volatile like synapses, so this becomes actually biphysical synapse. And so all you have to change is basically the stuff around it. So the cores can remain, the technology can be remain, and all you have to do is change the interface to the arrays of those elements. And it's amazing. This has been a wonderful technology. Unfortunately, Intel and Micron missed the boat, and so they missed the opportunity. This could have been amazing. This cross-point technology that for realizing 3D integrated neuromorphic systems that do compute and memory. Instead, they use it for doing a glorified solid-state storage device, and that was the end of that. But fortunately, the community is continuing. And neuromorphic engineers have taken those crossbar arrays, the same type of, in this case, again, phase change memory, and implement then spike time independent plasticity, right? Because in addition to inherently, by having these crossbars, you also have massively parallel operation. So there's, with an n by n array of those, you get n square operations done in one clock cycle, or even without the clock, asynchronously, right? And this STP, spike time independent plasticity, can directly be implemented by basically controlling the peripheral horizontal and vertical lines, basically activating and changing conductance. That is a function of the relative timing between pulses that you have at the input and the output along vertical and horizontal lines. Worked by Duike Kuzum and Philip Wong's lab many years ago, but now we're continuing now integrating those crossbar arrays with coarser arrays of those neurons, those integrated fire arrays that I just mentioned, right? That then can get events in, get events out, and here's now one core where you have, let's say, 16 by 16 neurons. That gives you 256 neurons in and neurons out, and then a finer grid of those crossbars over it. That gives you then this 256 by 256 grid of synapses, and then you can have direct vertical interconnect between the neurons and the synapses in a scalable way. And in fact, so you can then make that connectivity bidirectional. So that's a chip that we, this is RAM, resistive RAM or Memristive technology, but it's the same principle, right? So where you have then your metal oxides in the higher metal stack back end of the line. But same principle, here you have selected elements also, right? So here's a subcore here of those typical memory elements that you have. And then just have around it, you have this neuron that can be reconfigured. Either you connect to your inputs to a vertical line or to a horizontal line, right? So that you have this crossbar array here of synapses, and then you can actually direct the flow, right? And so notice that in this subtiled organization, each subcore has 16 by 16 synapses, and each connects to one unique line. So along the column here, right, all 16 lines are tapped by all of the 16 cells here, and conversely, right, all the cells along the horizontal line are also tapped by unique horizontal line. And so this way, every line connects to a unique, right? Every vertical and horizontal line connects to a unique cell. And locally, you can then redirect the flow. So normally you would have a whole set of peripheral cells implemented, so your input neurons that you have at the bottom of the array, and then you have your output neurons on the other side of the array, and then those are long and skinny cells. So now you have, I guess, more reasonable aspect ratios of cells, I guess, in fact, square geometries that implement your 26 neurons inside in this entire core. But more importantly, you can actually redirect the flow from inputs to outputs by simply flipping a switch here. The neuron can just basically flip a switch, and this way you can then backpropagate activity, right? So back from outputs to inputs, and that's important, say, for backpropagation learning, but also for other types of network architecture that now become increasingly important. You can do generative processing, reverting the flow of the network, so you have bottom-up and then top-down expectations, right? You can do generative learning as well as inference, Bayesian inference, basically in a variation autoencoder or Boltzmann machine fashion, just naturally by just flipping a switch through the architecture. And so we can do this at really great efficiency, so that's how we got about at a 13 femtojoules per synaptic operation. So owing to this processing here being done, those neurons are voltage sensing as opposed to current sensing. And I can point you to some more details in the paper. But that really brought, so rather than having this power-hungry transimpedance amplifiers that you have trying to voltage clamp the lines as you activate the conductances, you can simply sample them on a capacitor and then dump it onto this slower capacitor-based TIA integrator at much greater efficiency. And that's how we got femtojoules, as opposed to typical pico or nanojoules that was realized earlier. And so here's an example of how this can really pan out for generative inference as well as learning. And in a Bayesian sense, inference and learning are the same thing. And so you can have this you can go back and forth between from your visible units, right, to do your inference, to your hidden neurons here. There's a forward path. In the backward path, you can go back from, so once you figure out something, let's say you figure out a digit that you're classifying, now you can go back and reconstruct the pixels and then fill in the blanks that you have here of, say, occluded pixels, right? And that is a powerful framework that has become more important, whether it's stable diffusion or with transformers. Generative processing has become the hallmark of modern machine learning and AI. And this is naturally implemented here, right? In this you can go back and forth between layers, I guess, in conjugate directions. And so here is showing this in operation, almost virtual real time, where we have this running. So in this case, you present a digit 6 in this case, you occlude a few pixels. This was a demo at ICNCE a few years ago. And then it not only does it recognize as a digit 6, but also then it reconstructs it and gives you the best template that it found in your database, not as a template, but actually as the internal latent representation that you have in the hidden units, right? And it does so at much lower energy than when you do in a digital compute on a digital processor. And so we took this further by integrating in a whole array right, of those cores. In this case, we had 48 cores on one chip, and it gives us now 3 million RM cells and around 20,000 or so neurons implemented in a totally reconfigurable manner, because you can then redirect flow between output neuron activity to input neuron activity of other cores. And this way you can implement, in principle, general AI kind of applications. And so we demonstrated in multiple benchmarks, whether it's LSTMs or Boltzmann machines or so different architectures were implemented and different tasks were implemented by basically reprogramming the chip for different tasks. And we're able to get not only great efficiency, as I mentioned, but also being able to achieve accuracies that are comparable to the accuracy in digital emulations. So this is important because typically you have to choose right? And the prevailing paradigm was that choose between efficiency and programmability, right? So if you want to make it programmable, just go for your standard GPU or FPGA system. You pay price in energy efficiency. If you want to have really low power, low energy, then you go for a dedicated chip. So this shows that you can get both. You can have a general purpose system with crossbars that are extremely efficient, but then the communication between them gives you the power to do in principle anything and not really get too much penalty from the imprecision that you have inherently in those in the realized elements that are pushed to extreme efficiency, right? So you map basically your architecture of your network, whether it's feed-forward or recurrent, whatever it is, onto this tiled organization of, right? And you map it, and then you program it, and then you just measure what it does, right? But importantly, there is that you don't just program, but actually we program weights one layer at a time, and then retrain the remainder of the network to correct for the imprecision that is being due to the analog realization of your network. And so then each time, so as you go from one layer to the next, the retraining, the retuning of the remaining layers allows to accommodate then the imprecisions of the previous layers and almost recover the imprecisions, the precision, because within a percent, say, of the software emulated, software simulated performance. And it's important to know this is all accounting for the physics, also inject noise, similar noise that we expect during the inference, during the learning process. And every element is only programmed once, right? So after you program the first layer, you don't touch it anymore, you move to the second layer. So you still only is one pass to your network for programming. You just do a bit more fine-tuning in the background, which is fast in the process of programming your chip. And so this way, so gives you great performance as well as a general versatility and then efficiency, right? Now, for learning, I haven't said much about learning, but so injecting noise during the learning process is extremely important. They can even take advantage of the intrinsic noise that is present in your network, and you can emulate, directly physically emulate, whether it's a Boltzmann machine or variational autoencoder or right, a different system or a Bayesian system that assumes noise or stochastic encoding. Our brains have extremely stochastic elements. In fact, our synapses fail about 50% of the time. So the probability of a synapse actually doing this percent conductance is about 50%. And that's an amazing drop-out rate or drop-connect rate. Now, AI systems actually use the same principle of injecting noise in the training process for improving the generalization performance of your network. In this case, you get both. You can get greater generalization performance, but also more robustness to the intrinsic variability in the network, right? By actually living with the noise. Don't fight the noise, just use it. Take advantage of it. So then, and synaptic noise in particular is great. In fact, synaptic noise gives greater performance than neural noise in this, we call this synaptic sampling machines as opposed to the Boltzmann machine implementation that we have. Even get better performance because in terms of accuracy at lower operations for doing so, right? So there's definite advantage of using, and so intrinsically, so we have synapses that are probabilistic, both during learning and during inference, and so that's how we can really make great advances. A few words about efficiency. I mentioned femtojoules per multiply cumulate. Well, you can also get, you can even get attajoules of efficiency if you don't use resistive crossbars, but if you use charge domain or capacitive or mem capacitor, whatever you call that, crossbars. In this case, where you have charge storage locally and then you move charge non-destructively, right, from an input line, from an input, I guess, well here to the output, right? And this sends them not really transferred to the output, it's capacitively coupled to the output. So it only sits, the charge only moves locally. as in a CCD device. We call it a CID device, charge injection device. And then you also have local storage here for that bit of information or analog information that you have. And you can even recycle the energy that it takes for transferring that charge. So not only is it charge conserving, it's also energy conserving, in that the CV squared energy is actually preserved in the process of doing the operation. And so then you can get beyond the typical limits that you have, the dynamic energy consumption that you have in digital systems. And that's how we're able to get femtojoules per multiply cumulates, even in ancient technology 20 or so years ago. And now the latest work is we realized down to 10 attojoules per multiply cumulate, so 100 times better than the nominal efficiency of the brain. At the device level and at the system level, including all the periphery, right, circuits, then you get basically 100 attojoule per multiply cumulate. That's basically by recycling the energy that you have, right, that you have this energy recovery logic drivers, so recycling the capacitive energy in the inductor they have coupled on the outside. And so at resonance, you can recover most of the energy in your compute. Does the brain do this too? I would actually argue in some way, yes. Brain waves that you have, theta cycle, maybe there's something about a theta cycle, but it's fine. As engineers, we can invent other things, it's okay. So most of our work we enable for the community. Here we have the system with 40 FPGAs that do reconfigurable neuromorphic computing. That gives a net bandwidth of about 20 terabytes per second. So there's about 4 tera synaptic operations per second that is realized in the system at scale. So with 160 million neurons and 40 billion synapses, owing to this high bandwidth memory that you have for each core, right, and then replicated for 1,000 cores in the system. This is available over the neuroscience gateway, so anyone can go in there and send their Python code and emulate the network, and then have it run much faster on the hardware. And so with that, I'll just thank you for your attention. And the slides are copied here, so you can also download that if you like. And any questions, please, and I look forward to hearing you again.
Thank you very much, Gert, for this inspiring talk. We have maybe time for one question. Okay, this is good because we are a bit short in time, but there's one question that is really intriguing me, Gert, so I will ask it myself. So on one slide, you seem to suggest that machine complexity has already surpassed the complexity of the human brain. Can you maybe elaborate on this in a few sentences?
Well, not the complexity, but the efficiency, yes. So the efficiency, so now we're down to attojoules per synaptic operation, or per multiply cumulate. Let me actually write, a multiply cumulate is much less than a synaptic operation. There's much more involved, right? Plasticities, right? But normally by that metric, yes, we're beyond that. And it would be a shame if we can't, right? Because clearly electrons with a great high mobility moving through silicon, it must be more efficient, right? Of course, there's much more work to be done to actually realize that intelligence, right, and at the system level. And so that's why we're all here to make advances in the field.
Okay, thank you. So let's thank our speaker again.